Okay, so our next speaker is Karl Broman, professor at University of Wisconsin-Madison and in biostatistics and medical informatics, and he's going to talk to us about data cleaning principles. Over to you, Karl.
Thanks very much. Just trying to reorganize my stuff here. As an applied statistician, I spend a lot of my time cleaning data, and I think many of you do as well. But have any of us had any formal training in data cleaning? I don't think there are many courses that talk about data cleaning, or publications for that matter. Some say it's because it's difficult to generalize. Hadley Wickham said that tidy data are all alike, but every messy data set is messy in its own way. But is this really true? Is every messy data set uniquely messy? My collaborators are pretty creative in their handling of data, but we do see pretty much the same problems repeatedly many times. Roger Pang asked, if I clean up Medicare data, does any of the knowledge I gain apply to the processing of RNA-seq data? My response is absolutely. The context clearly matters, but cleaning one data set provides a lot of really useful experience when you come to the next one, even if it's from a completely different field. One of the best things that happened during the pandemic was Data Mishaps Night, an online conference where there were a bunch of 5-minute talks about basically people talking about their experience screwing up data. Many of the mishaps people have had that discuss concerned problems in data cleaning. And there was really a strong shared experience in that data, in our struggles with data. And I think in many ways, data analysts have more in common in our approaches to handling data cleaning than we do in, our actual, data analysis after, itself. I think data cleaning is not taught because it's tedious. The results are often embarrassing. You do need the context, and often it doesn't really feel like progress. How many students are going to sign up for a course in data cleaning? On the other hand, it requires great creativity and some of our really fanciest programming skills. And if you screw it up, it really has a big effect on the results in a bad way. Well, if you do it well, it also has a big effect on the results in a good way. So I really do think that there are principles to data cleaning, and so I'm going to propose some to you today. I've split them into 5 groups: some fundamental principles, followed by what I group as verify, explore, ask, and document. The first fundamental principle is don't clean data when you're tired or hungry. Ghazal Gulati said this at that first Data Mishaps Night, and it's right on. Cleaning data requires intense concentration, takes time. So, grab a snack, get a cup of coffee before you start. The second principle is don't trust anyone, even yourself. Maybe a person you really respect compiled the data. Maybe it was you 3 months ago. Still, you should double check. Jenny Bryan once tweeted, "My motto is trust no one except maybe KW Broman," which I think may be the nicest thing anyone has ever said about me. But still, don't trust him either. Really, a central principle for me is to think about what might have gone wrong and how it might be revealed. And this illustration is from what's probably my most dramatic data cleaning success. I think Many of you may recall this genetic study where almost 20% of the samples were mixed up. The samples were, arranged on these 8x12 plates, and a dot is indicating that the correct sample was in the correct spot, and an arrow is pointing from where a sample should have been to where it actually ended up. So in this study, there were a bunch of long range sample swaps and then a huge number of off by 1 and off by 2 errors. But the way that I came to this realization, the way I identified these sample mix-ups was following this basic rule of think about what might have gone wrong and how it might be revealed. And hopefully it's not this. A fourth principle is to use care in merging data files. I think a lot of the mistakes that we make have to do with assumptions about files and when we merge them. So here are a couple of files where the columns have changed order. And if you don't take that into account, you're going to screw it up. And I think there's sort of a corollary is that focus on the labels rather than position is often a key thing to do. The fifth fundamental principle is that dates and categories suck. You're going to spend a lot of your time trying to fix typos and inconsistencies in dates and categorical variables. And you may be thinking, wait, how is that a principle? I mean, I was thinking that too. What exactly is a principle? Now, my working definition of principle is that it's a fundamental truth that guides our thinking. And with that definition, dates and categories suck, totally a principle. And just be glad you're not dealing with time zones. Moving on to the next category, verify. You want to verify everything that should be true about the data really is true. And so principle 6, check that things that are supposed to be distinct really are distinct. So here in this data set, the ID column, those are supposed to be all distinct values, and there are a couple values repeated. One of them turned out to be a typo. And 7, check that things that are supposed to match really do match. So here are a couple data files, an individual where in one file it was said to be in the 22nd generation and another file was in the 21st generation. So these two columns are repeated in 2 data files. They should be all the same. You should check that they really all are the same. Next, any calculations that have been done, you should check that they're correct. Here's an example on the panel on the left, a plot of Homo IR. This is supposed to be the product of glucose and insulin. So if that's in a file, you could calculate it directly by taking the product of glucose and insulin. You plot those two against each other. It should be like this, all the same. Here, I've pulled out missing values into the margins rather than just omitting them from the plot. And there are some values where the product of glucose and insulin is observed as a distinct value, but it was missing from this column Homo IR. So that is a little weird and something to check on. But also, when you're looking to see whether two things are the same, or you're looking to see if there are differences between your calculation and the calculated thing previously in the data file, it's often best to just calculate the differences and look at them directly. So I take, subtract the 2 and plot those, and you do see, things are the same up to some round off error. There's a batch of values that are maybe more coarsely rounded, often a signature of some copy paste job that happened. There's also a batch of data points that are missing that could be the same as this batch that are, where you have glucose and insulin themselves, but not their product. But any calculations, you should check that they're correct. It helps to both make sure that things are right and to check your understanding. And then again, the next principle is look for any other instances of a problem. If you find a problem in the data, look for could that have happened anywhere else? It's similar to trying to find bugs in code. If you find a bug, you should say, have I made that mistake anywhere else, and look for it actively. The next section, explore. You want to, having verified that what was true actually is true, then you want to explore the data more generally. And a key principle is just to make a lot of plots. Plot things against time or sort of in the order they appear in the data will show, batch effects like you're seeing here. Plot things against each other. This is 6-week body weight plotted against 10-week body weight. There are a couple mice one that really went down in weight and another one really went up in weight. It turned out to be just a couple of data points transposed. One of the main things you're looking for are outliers. In this plot of adipose weight against mouse index, there were a group of values that were given in grams instead of milligrams. There's also maybe some kind of batch effect going on there. And another principle is just to look at the pattern of missing values themselves. There are a couple R packages that are useful for this. VisDat will give you kind of a heat map that shows which values are missing. That can be useful. This package will make scatter plots similar to what I showed before, but that instead of omitting missing values, it shows them in the margins. And when you have really large data sets, you should be making more plots rather than fewer plots. Often you say to yourself, I can't look at 500 histograms, but in fact, so you end up looking at no histograms, but in fact, you can look at 500 histograms. Oops, sorry. You can, put 25 on a page and flip through 20 pages, or you can make density estimates and plot them superposed like this. You could maybe highlight some of the distributions that are more variable to see if there's a cluster of very different ones, or for each distribution you could pull out like the mean and the SD and plot those against each other. Or here, for that same data, I'm plotting the interquartile range against the median, and you can see that there's a batch of distributions that are really quite different from the others. It turned out to be a batch of microarrays that were bad. And then follow up any artifacts. If this is a heat map with rather poor choice of colors and a weird Scotch plaid pattern, that's just to remind you, like if you see an abomination like this in your data, you should say what is going on here, and really don't let it go until you figured out what is going on. I'm running out of time, or I've already run out of time, so I'll just zip through the last. You should ask questions. Ask for the primary data, ask for the metadata, like what the heck are these data? Ask why data are missing. Are they missing because something went bad? Is their missingness informative? Is it going to bias my results? And document what you did. Use the experience that you had in data cleaning to create checklists and pipelines that will help you to find those kinds of mistakes better, more rapidly the next time. And then document not just what you did, but why you did it. It really needs to be more than just reproducible analysis. You need to capture the why you chose to do what you did, or why you made the decisions you did. And data cleaning is not just a step in the data analysis process, but it's sort of an ongoing thing that you're going to return to as you learn more about your data. So expect to be going back and redoing everything again. And so, that's my 20 data cleaning principles suitable for posting on your laboratory wall. Alison Reichel tweeted, "I will let the data speak for itself when it cleans itself," which every time I read that, it just gives me a little jolt of joy. That data, it's not going to happen. The AI is not going to clean our data for us. We're going to be cleaning data for the rest of our careers. Yeah. So, well, thanks. Thanks for making it possible for many of us to present remotely. And here's where you can find me in these slides.
We are out of time, but we can have a quick question and then I'm expecting we'll have 10 minutes at the end of the session. So if there's a quick question.
So Karl, great. Karl also has a wonderful link to how to abuse and use Excel. So how many, I assume most of you or all of you use Excel with some exceptions. But definitely check out, Karl, do you have that link? Can you put that in
I'll put it in the chat.
Yeah, thank you. Because I can't tell you how much grief it would save me if people took this, Karl's comments on Excel abuse to heart.